Good morning, everyone. Myself, Dr. Amit Shrivastava. I am professor in CSE department, SIIT Bhopal. So this is the second lecture on neural network, which is in continuation with my first lecture. So previously, we have already seen, what are linearly separable problems and how the gradient descent principle works, what is the backpropagation technique, and how we apply the backpropagation technique in the neural network to solve this numerical, right? Now, let us look at actually the how we do the weight updations. So in this lecture, we will be focusing on how we are going to update this weights W1, W2, W3, W4, and W5, W6, W7, and W8, so that my error becomes less as compared to the previous errors. So the same numerical we will be working on in this lecture. Okay. Now, this is my numerical. This is my data. Now I want to update this weight W5. Let us assume this is the weight W5 which I want to update. So what will be the formula as per my gradient descent principle? My formula will be like this. W5 new will be equal to W5 old minus alpha, that is my learning rate, into del E total upon del W5. So it means I have to calculate this del partial derivative of total error with respect to this partial derivative of W5 for updating my weights, right? So let us see how we can do it. Okay. So this weight W5 is coming to this O1. Okay. Now this O1 is getting the output of H1 multiplied by this W5, output of H2 multiplied by this W6, and this bias. All these are the inputs to my O1 output neuron, right? So here we can see W5, W6, and B2 is coming to this O1, and my total input O1 we are receiving will be, we will apply this sigmoid activation function over this total input at O1 to get the output of O1, right? So partial derivative of E total with respect to W5, this is what we need to calculate, right? That is, what is the change in total error with respect to this weight W5. So we cannot directly differentiate this total error with this W5. So we have to find some relation for that. Now, first of all, let us see. My total error is nothing but EO1 plus EO2. EO1 can be written as half into the target, that is my actual output, minus the predicted output, the whole square. Now, out O1 is the sigmoid function, 1 upon 1 plus e to the power minus x applied over the total input. So 1 upon 1 plus e to the power minus in O1. Now, in O1 is what? In O1 is nothing but, you can see from here, in O1 is what? H1, out H1 into W5 plus out H2 into W6 plus B2, right? So in O1 is out H1 into W5 plus out H2 into W6 plus B2 into 1. Now, del E total upon del W5, we can rearrange this using the chain rule so that we can establish some relation, because we cannot directly differentiate this total error with this W5 because it is not directly related. So what we can do is del E total upon del out O1 into del out O1 upon del in O1, and then del in O1 upon del W5. So what happens? This del out O1 and this del out O1 will cancel out. This del in O1 and del in O1 is cancelled out. So we are left with only del E total upon del W5, which is my left hand term, right? So we can apply this chain rule here. Okay. So Now, E total is half of target O1, that is my actual output from which is coming from O1, minus out O1, that is my predicted O1, the whole square, plus half into target O2 minus out O2, the whole square, right? Now, when I do the del E total upon del out O1, then what will happen? When I partially derivate this with out O1, so what I'm actually calculating, this term I'm calculating, del E total upon del out O1, first term I'm calculating, right? Del E total upon del out O1. So this 2 will come out. So half into 2, then target O1 minus out O1 into, when I penetrate this inside, so when I partially derivate this target O1 with out O1, then this will be treated as constant and it will become 0, minus out O1 with respect to out O1 will give me 1, right? Plus this total term is not connected with this out O1, so it will all be treated as constant and it will become 0. So this will be 0. So now I'm left with this 2 and 2 will be cancelled out. So I'm now left with target O1 minus out O1 into minus 1. Okay. So minus of target O1, as we have already seen in the example, my actual output was 0.01 and my predicted output was 0.75136. So this is my value which is coming 0.74136. And this is my first term, del E total upon del out O1. Okay. Now we need to calculate the second term, that is del out O1 upon del in O1. Okay. So out O1 is nothing but 1 upon 1 plus e to the power minus in O1. Now 1 upon 1 plus e to the power minus x. Let us assume that in O1 I'm considering as x, my input, my x equal to, and this out O1 is nothing but my f of x, right? So fx is equal to 1 upon 1 plus e to the power minus x can be written as 1 upon 1 plus e to the power x. So this will go up. So e to the power x upon 1 plus e to the power x. Now this dfx upon dx, my n01 is nothing but my x, which I'm considering here. So what I can write this term as del out O1. Del out O1 I'm considering as fx. So it means del of fx upon del of x equal to e to the power x upon 1 plus e to the power x the whole square. When I differentiate this, then I will get this output. Now I can write this term like this, e to the power x upon 1 plus e to the power x into 1 upon 1 plus e to the power x. So this e to the power x upon 1 plus e to the power x is nothing but my fx. We have seen here. So it is nothing but fx. So I'm writing it here as fx. This term can be written as 1 plus e to the power x minus e to the power x upon 1 plus e to the power x. So this left hand term 1 upon 1 plus e to the power x upon 1 plus e to the power x will cancel out and it will become 1 minus. In the right hand side, we are left with e to the power x upon 1 plus e to the power x, and it is nothing but fx. So fx into 1 minus fx. So when I partially derivate this del out O1 upon del in O1, then I'm getting this as my output. So it is nothing but out O1. Fx is nothing but my out O1. So out O1 into 1 minus out O1. So we already know the values of out O1. It is 0.75136. So we just put it the values and we can get 0.18681. So this is the output, my second output of my second term. Okay. Now we need to calculate the third term. My third term is del in O1 upon del W5. So del in O1 upon del W5. My in O1 is nothing but out H1 into W5 plus out H2 into W6 plus B2 into 1. So del in O1 upon del W5. When I partially derivate this with W5, then the output of this will be out H1 plus this out H2 will be treated as constant. So when I partially derivate it with W5, it will become 0. And this bias is also a constant. So it will again become 0. So it means del in O1 upon del W5 is nothing but out H1. And out H1 we already know it is 0.59326. So this is my third term. So now my actual formula was del E total upon del W5, and we have already calculated all these three terms. So just putting it the values, we will get this as my final output. So now we need to update the weight W5. So the formula we already know, W5 is W5 minus alpha into del E total upon del W5. Let us assume that I am taking alpha as 0.5. So we just put in the values, W5 is 0.4 minus alpha is 0.5 plus this is the term we have already calculated just now. So we multiply it and we get the updated weight of W5 is 0.35892. The previous weight was 0.4, right? In the similar fashion, we can also update the weights W6, W7 and W8 the same manner. So now let's look at the diagram. So W5, W6, W7 and W8 we can update in the similar manner. Now we need to update the weights W1, W2, W3 and W4. So let us see how we can update the weight W1, and once we update the weight W1, then we can similarly update the weights W2, W3 and W4. Okay. So here this H1 is getting the I1 multiplied by W1 plus I2 multiplied by W2 plus this bias. Okay, so this is the total input which we are getting at H1, and out H1, how we are going to get the sigmoid function applied over the total input, that is 1 upon 1 plus e to the power minus in H1. This will give me the output, right? Okay. Now, del E total error upon del W1, because the formula for updating the weight W1 will be W1 equal to W1 minus alpha into del E total upon del W1. So we need to calculate this term del E total upon del W1. So now del E total, the total error with respect to W1 cannot be directly done. So we again need to apply the chain rule. So we can do like this: del E total upon del out H1 into del out H1 upon del in H1 and del net H1 or del in H1 upon del W1, right? Okay. So del E total upon del W1 is del E total upon del out H1 into del out H1 upon del in H1 plus del in H1 upon del W1. Now let us see this term del E total upon del out H1. So del E total upon del out H1 again is not directly related, because out H1 multiplied by W5 will be giving me the in O1, and the out O1 is directly related to this total error. So what I can do is del E total upon del out H1 is del E O1 upon del out H1 plus del E O2 upon del out H1. EO1 is half into target O1 minus out O1. Target means my actual, and this is my predicted O1 output, the whole square. Out O1, we already know that out O1 is 1 upon 1 plus e to the power minus in O1, right? Or in O1 is what? W5 into out H1 plus W6 into out H2 plus V2 into 1. We already have calculated this formula. Now, let us calculate this term del EO1 upon del out H1. So del EO1 upon del out H1 is del EO1 upon del out O1 into del out O1 upon del in O1 and del in O1 upon del out H1. Now these terms are related to each other. So del EO1 upon del out O1 and del out O1 O2 del out O1 upon del in O1. This we have already calculated in the previous case when we were updating the weight W1. When we were updating the weight W5, right? So we have already calculated these terms. We can see in the previous lecture. So now we need to calculate this del in O1 upon del out H1, right? So del in O1 upon del out H1. So del of in O1 in O1 is this. So when I partially derivate this with out H1, then output of this term will be W5 only. So W5 into out H1 upon del out H1, output will be W5 only. And when I partially derivate this W6 into out H2 and B2 into 1 with this out H1, then it will be treated as constant and it will give the answer 0. So final output of del N01 upon del out H1 is nothing but W5. So del E01 upon del out H1 is these two terms. We have already calculated the first two terms. So we can take the previous values and then this W5, which is 0.4. So we get the output of del E01 upon del out H1 as 0.05539. Similarly, we can calculate the del EO2 upon del out H1. It is coming to be minus 0.019049. So now what del E total upon del out H1 is del EO1 upon del out H1 plus del EO2 upon del out H1. So we will simply add these terms, and finally we will get the term as 0.036350. So till now we have calculated the first term of this equation. So del E total upon del out H1 into, this is my total terms, del out H1 upon del in H1 plus del in H1 upon del W1, right? So now out H1 is 1 upon 1 plus e to the power minus in H1. So when I do del out H1 upon del in H1, then we have already seen the relationship between this in our previous lecture, that we can write this as like this. Del out H1 upon del in H1 can be written as out H1 into 1 minus out H1. So just putting out the values, we can calculate this value. So it is coming to be 0.24130. Now the third term, del in H1 upon del W1. So in H1 is nothing but W1 I1 into W2 I2 plus B1 into 1. So when I partially derivate with W1, then these two terms will become 0 because this will be treated as constant with respect to W1, and this will become I1. So finally I'm left with I1. So I just put the value of I1, that is equal to 0.05. So now I've got all the terms of 4, 5 and 6. Putting the values, we can calculate the del E total upon del W1. So it is coming to be 0.0004385. So for updating the weight W1, we will use the same formula. For W1 is equal to W1 minus alpha, that is my learning rate, into del E total upon del W1. Just putting up the values, we get the W1 updated W1 as 0.14978. The previous value of W1 was 0.15. So it has updated a little bit. In the similar fashion, we can calculate the W2, W3 and W4 also. The same process will be followed. So finally, we have updated all the weights, and then we again calculate the final error. And here, the total error, in pass 1, the total error was 0.29837. And now with this updated weights, we are, when we calculate using the same formula, then we will be getting the error as 0.29102. So we can see here that it has reduced a little bit. Okay. So it will definitely reduce, but it will reduce the error will be reduced in a very gradual manner, because we are also making use of alpha, that is the learning rate. Now this error is reduced but very less, and after 10,000 passes, if you calculate and apply this formula, so after 10,000 passes, the total error will remain as 0.0000351085. So this is how we apply the backpropagation technique in the neural network. Thank you.